So we have seen the first fundamental theorem of calculus in the last lecture. Very loosely speaking, it said that if small f is a continuous function defined on an open set omega, which has an antiderivative capital F, and if gamma is a rectifiable curve whose image is contained in omega, then integral of small f over gamma is equal to capital F of z2 minus capital F of z1, where z1 and z2 respectively are the initial and the terminal points of gamma. In this lecture, we will be proving a second fundamental theorem of calculus, which is the complex analog of the second fundamental theorem of calculus, which you would have already seen in the real setting. But before we do that, let us recall the equivalent formulation of open connectedness in the complex plane. So, recall the following are equivalent. We had given more than one equivalent formulations. What were those? So, for omega contained in C open, the following are equivalent. What was the first one? Omega is connected. What was the meaning of a subset of C being connected, or rather subset of a metric space being connected? It means that the set omega does not have a separation. We say that omega has a separation if we can write it as a disjoint union of U union V, where U and V are non-empty open subsets of omega. So, we say that omega is connected if it is not having a separation. What was 2? 2 said that an open connected subset of C is always path connected, and it is equivalent to demanding that it is connected. Omega is path connected. What is the meaning of path connected? It means given 2 points z1 and z2 in omega, there exists a curve gamma whose image is contained in omega such that the initial point of the curve is z1 and the terminal point is z2. And the third is that omega is polygonally path connected. What is the meaning of polygonally path connected? A polygonal path, if you recall, polygonal paths. Path is the concatenation of straight line paths. In fact, we had proved a slightly stronger result than just demanding that it was polygonally path connected. If you go back to the first week and look through our lectures, we had proved that these polygonal paths can be arranged in such a manner that each of the line segments featuring in the polygonal path is parallel to either the real axis or the imaginary axis. So, we had proved something in fact stronger than what is written here. So, typically polygonal paths are written in this manner. Is a polygonal path is used to denote a polygonal path. A polygonal path obtained by the concatenation, obtained by concatenating the straight line paths, the lines joining, let me just write it informally as zj to zj plus 1. So, I will leave it to you to give a correct parameterization, or rather the domain of definition of such a gamma when straight line paths are already given to you. Okay, so let us now get down to proving the second fundamental theorem of calculus. So, what is the complex analog of the second fundamental theorem of calculus? To describe the complex analog, let us recall what the real analog said. Real analog of the fundamental theorem of calculus, second fundamental theorem of calculus, said the following. If we have a function small f which is defined on a closed interval a b into r, and if we define capital F of x to be integral from a to x f of y dy, then this function capital F is an antiderivative of small f, and we can say that f capital F prime at any point x in a b is equal to small f of x. So we will give a very analogous statement here, but keeping in mind now that we are in the complex setting. So we will need to add an additional hypothesis to the statement of the second fundamental theorem of calculus. Let me write down the statement. Let omega contained in C be an open connected subset. This is what is usually referred to as a domain or a region in many textbooks. And let small f from omega into C be a continuous function such that the integral of f over gamma is equal to 0 whenever gamma is a closed polygonal path. Gamma is a closed polygonal path contained in omega. So if you sit down and think about the real setting, this condition is automatically satisfied there. Let's fix a base point z0. Fix z0 in omega and define capital F of z1 to be equal to integral over gamma of f of z dz. Now gamma is a polygonal path from z0 to z1. Notice that there is a choice involved here. We will get to that. We will talk about well-definedness in detail in a minute. What is the conclusion? Then capital F is well-defined and is a well-defined holomorphic function such that it is the antiderivative of small f. Capital F prime of z1 is equal to small f of z1 for all z1 in omega. Let's go over the statement once more very carefully. So let omega be a open connector. Let me just add non-empty as well. Be a non-empty open connected subset of the complex plane, and our function capital F satisfies the condition that if you look at any closed polygonal path which is contained in omega, then the integral of f over gamma is equal to 0. Then if we define our function capital F at any point z1 in omega to be integral of f of z dz over some polygonal path from z0 to z1, then that capital F is going to be an antiderivative of small f. That is what the statement of this second fundamental theorem of calculus tells us. So notice that this condition that integral of f is satisfied to be equal to 0 for any closed polygonal path, that is something which is naturally satisfied by any function which has an antiderivative. So if small f has indeed an antiderivative, the first fundamental theorem of calculus will tell us that this condition is automatically satisfied, but we are putting this in the hypothesis here. Let's get to proving the second fundamental theorem of calculus. We will start by noticing that the function we have just defined above, that's a well-defined function. So let's first target the well-definedness. Why is there a question of well-definedness? Suppose we have two polygonal paths, gamma 1 and gamma 2, the polygonal paths from z0 to z1. Remember that z0 is a fixed point in omega, and it is at z1 that we are trying to define capital F. Then notice that gamma 1 and gamma 2 both have the same initial point and the same terminal point. In particular, if you look at gamma 1 plus minus of gamma 2, this is a closed polygonal path. Concatenation of two polygonal paths is again going to be a polygonal path, and now the initial point of the curve gamma 1 plus minus gamma 2 is the reversal of gamma 2. So if you look at the initial point of gamma 1 plus minus gamma 2, that is going to be the initial point of gamma 1, which is z0, and the terminal point of this curve will be the terminal point of minus gamma 2, which is the initial point of gamma 2, which is again z0. So this is indeed a closed polygonal path. Now, by invoking the hypothesis of our theorem, we get integral of f over gamma 1 plus minus gamma 2 is equal to 0, because it's a closed polygonal path. But now we will use the properties of the integral defined over integration of functions over rectifiable curves. We can say that this is equal to the integral of f over gamma 1 plus the integral of f over minus gamma 2. We further use the property of the integral of f over the reversal of a path being equal to the negative of the integral of f over gamma 2, and hence integral of f over gamma 1 is equal to integral of f over gamma 2, because this is equal to 0. So it doesn't matter what polygonal path we pick from z0 to z1. Irrespective of what polygonal path we pick, the integral is going to be the same, and hence the function capital F of z1 is well defined. What next? The next part of the theorem said that this capital F is a holomorphic function. Not only is it some arbitrary holomorphic function, it's exactly the antiderivative of small f. In other words, capital F prime of z1 is the same as small f. We will show that the derivative exists at the point z1 and that the derivative is equal to small f in one go. So let's take a point z1 where we would like to show the complex differentiability. Let z1 be in omega, and let dz1r be a disk which is contained in omega. Remember that omega is an open set, so there exists some r such that this certainly happens. Each point is an interior point. Then let us look at a particular polygonal path from z0 to z1. Let sigma or let gamma be a polygonal path from z0 to z1, and pick some point z2 in the disk of radius r around z1, and gamma z1 z2 be the straight line path which joins z1 to z2, be the straight line from z1 to z2. I'm going to use the operations on these curves quite freely, which I hope you are now comfortable with. Then gamma concatenated with gamma z1 to z2, this is a polygonal path because it's a concatenation of polygonal paths. This is going to be a polygonal path from z0 to z2. Now let's invoke the definition of capital F, and let's look at what is capital of z2 minus capital of z1. What was capital of z2? That is going to be the integral over some polygonal path from z0 to z2, which we now have very explicitly one such candidate, this is of f of z dz minus what is capital F of z1? That's going to be integral of f of z dz over a polygonal path from z0 to z1. So this is the exact difference f of z2 minus f of z1, capital F of z2 minus capital F of z1. And again, using the properties of the integration over curves, this is going to be integral of f over gamma plus integral of f over gamma z1 to z2. And I'll just directly write this as integral of f of z dz over gamma z1 to z2. Okay, we know exactly what we are trying to estimate. We know what we want to prove. So we know that capital F is the candidate for, or rather, small f is the candidate for the derivative of capital F at z2. So let's try to estimate this. Small f of z1 times z2 minus z1. Let's try to estimate this. And by going down to what is written above, this is going to be equal to integral of the absolute value of integral of f of z gamma z1 to z2 minus f of z1 times z2 minus z1. So this is precisely what we get. And again, what will be the integral of a constant over a straight line path? It's just going to be what I am writing here. It's going to be integral of f of z1 times z2, sorry, integral of f of z1 dz from over a path gamma from z1 to z2, a straight line path gamma from z1 to z2. That's going to be exactly this, right? And by taking that into account, this is going to be f of z minus f of z1 into dz over gamma z1 to z2. But then f is continuous at the point z1, and by picking r small enough, we have absolute value of f of z2 minus f of z1 minus f of z1 times z2 minus z1. This is less than or equal to epsilon times the absolute value of z2 minus z1. Okay, we are almost done, because now if you look at the limit as z2 approaches z1, where z2 belongs to omega minus z1, z2 will eventually be in this disk of radius small r, and we will be able to say that f of z2 minus f of z1 by z2 minus z1, now z2 is not equal to z1, minus f of z1, this is less than or equal to epsilon. And our choice of epsilon was arbitrary. This means that hence limit z2 going to z1, z2 in omega minus z1 of, maybe I should have just written down directly, this is the same as demanding that capital F is complex differentiable at the point z1, and the derivative capital F prime at z1 is equal to f of z1. So in one stroke we have proved the entire result. Let's go back to the statement once more and notice what was the restriction that we however have put. We have put one hypothesis here. This is the only hypothesis that has been put on the function f, that integral of f over gamma is 0 whenever gamma is a closed polygonal path. Sometimes this condition is also referred to as demanding that f is conservative. I think the origins are from physics. Anyway, so one weakening or an equivalent formulation would be by weakening this particular demand that we have. Closed polygonal path. We have after all defined integral of f over rectifiable curve. So one might naturally ask, why bother just about closed polygonal paths here? The next proposition or the next result that we would be proving would be that if integral of f over gamma is 0 for all gamma which are closed polygonal path, it's equivalent to demanding that integral of f over gamma is 0 for all closed rectifiable curves. So let's get to proving that. So in order to prove that, let me just write down a proposition. The proposition is the following. So the setup is as above. Let omega contained in C be open connected, non-empty open connected. And f from omega into C be continuous, be a continuous function. Let gamma be a rectifiable curve. In omega from say z1 to z2, the initial point being z1 and the terminal point being z2. Then there exists, given epsilon positive, there exists a polygonal path sigma from AB to omega such that from again z1 to z2, the initial point is z1 and the terminal point is z2 such that integral of f over gamma can be made arbitrarily close to integral of f over sigma, or given epsilon positive, this can be ensured. The integrals are epsilon closed, that can be ensured. So notice that this is a strong condition in the following sense. If we know that integral of f over all closed polygonal paths is 0, and if we take a closed rectifiable curve gamma, then we can get a polygonal path sigma which satisfies this condition for every epsilon, and the integral of f over a polygonal path is 0 all through, and therefore we get that the integral of f over gamma is absolute value of integral f over gamma is less than epsilon for all epsilon positive, and therefore we get that integral of f over gamma is equal to 0 for a closed rectifiable curve. So if we prove this proposition, what we would have essentially proved is that the hypothesis which is presented in the second fundamental theorem of calculus, that is equivalent to demanding that integral of f of z dz over gamma is 0 for all closed rectifiable curves, and we would be back in the same generality. Okay, let's prove this equivalence. Let's give a proof. So the first observation in this proof would be to get hold of neighborhood of the image of the curve which is sitting inside omega, whose closure is also a subset of omega. To do that, we observe that gamma, we know that gamma of the interval AB, which is the image, is a compact set. This is because continuous images of compact sets is compact, and let B, by invoking the compactness, let B Z0 R0 be, oh sorry, this is in our unit disk, so let me use the notation D for the disk. This is in the complex plane, and therefore let me use the notation D for the disk. dz1 r1 up to say dzn rn be let me call this something u, be a finite cover such that gamma of AB is contained in the union of dz0 r0 and dz0 r0 closure is contained in omega. That would ensure that the union of the closures is also contained in omega. So let K be equal to the union of dz0 r0 bar, then K is contained in omega, and by Hein-Borel theorem it's both bounded and closed, and therefore it's going to be compact. K is compact. So why did we get hold of one such subset? The main idea was to ensure that F is uniformly continuous on K. Because it's compact, since K is compact, F is uniformly continuous on K. Since F is uniformly continuous, we have a delta, maybe delta prime, or let's call it delta, such that the absolute value of f of x minus f of y, maybe x and y shouldn't be used, z minus w, this is less than epsilon by 2 times the arc length of gamma. We will see why this strange constant is being put. I just want epsilon at the end, it shouldn't matter. Anyway, so the absolute value of f of z minus f of w is less than this whenever mod z minus w is less than delta in K. Z and W both are points in K with mod z minus w less than delta. If that is the case, then uniform continuity ensures this. Okay, now since integral of f over gamma can be approximated by Riemann sums, let's pick a partition. Let P given by say a equal to t0 less than t1 less than up to say tn equal to b. This is the partition that has to be picked carefully. Let P be a partition such that the partition size, let me just partition size is less than the minimum of both delta and Lebesgue number of u. So let's just go up and check what the set u was. The script u, which I am underlining now, is this particular open cover, which is a finite cover of gamma of closed interval AB. Let me recall what Lebesgue number was for a given open cover. The Lebesgue number was a number, let's call it delta prime here because delta is already taken. Delta prime such that if you look at any disk of radius delta prime with center at a point in the image of gamma, that will be contained in one of these open sets which is given in this open cover. That was the precise definition of our Lebesgue number. So that Lebesgue number is being put here just to ensure that any point or any neighborhood of any point in the partition will always be sitting inside one of the open covers and hence inside K. Okay, we'll come to that. So let's pick the partition in such a manner that its size is less than both delta and Lebesgue number, and not just this, and such that the integral of f of z dz over gamma, this is approximated up to epsilon by 2 by the partition. Gamma of tj minus gamma of tj minus 1, this is less than epsilon by 2. Okay, now we have all the machinery to define our sigma. Let sigma be the concatenation of paths, be the polygonal path such that sigma restricted to tj minus 1 to tj. This is just the straight line path which joins gamma of tj minus 1 to gamma of tj. So let me just draw a picture for you. Suppose this is our omega, and let me draw a red curve which is our curve gamma. Suppose this is from z1 to z2, and our partition is by, say, these green points, t0, t1, t2, and so on. So I'm just going to pick points arbitrarily. So the assumption of this partition is that its partition size is less than the minimum of the two numbers above, and we are going to look at the lines joining these points, straight line path. So this is precisely our sigma. The green path, which is a polygonal path, is going to be sigma, and so maybe I shouldn't write equal to, it's just equivalent to the straight line path joining gamma tj minus 1 to gamma tj. This is very specific. This is basically 1 minus t times gamma of tj minus 1 plus t times gamma of tj, but this is not that way, so it's equivalent. So I'll just leave it to you to check the equivalence part carefully here. So sigma in the interval tj minus 1 to tj is going to be the straight line path from gamma of tj minus 1 to gamma of tj. My claim is, if we look at the integral of f over gamma minus the integral of f over sigma, the candidate now is sigma, so I would like to show that this difference is less than epsilon. So let me just look at this. This is going to be less than or equal to the integral of f over gamma f of z dz minus that Riemann sum which we had picked. So notice that in this Riemann sum I am picking gamma of tj itself. We could have picked any point from tj to tj minus 1 to tj. I am just picking it to be, or maybe I should pick tj minus 1, that may be better. It doesn't matter, any point should estimate it. So let me put a tj minus 1 here, and gamma of tj minus gamma of tj minus 1. So this certainly is there by triangle inequality. This is now less than or equal to summation f of gamma of tj minus 1 times gamma of tj minus gamma of tj minus 1 minus integral of sigma f of z dz. The first one is less than epsilon by 2. That is how we have picked our partition. Let's focus on the second one. I will write it in this manner. Integral of f of z dz over sigma minus sum of f of gamma of tj minus 1 gamma of tj minus gamma of tj minus 1. If you notice, I can rewrite this as being equal to the integral of f of z dz over sigma. Let me write j equal to 1 to n here, minus the sum j is equal to 1 to n f of gamma of tj minus 1 times, instead of gamma of tj, it's the same as sigma of tj, isn't it? And further, I can rewrite this as f of z dz minus summation j is equal to 1 to n integral of f of gamma of tj minus 1 dz, the constant f of gamma of tj minus 1 dz, integral over sigma restricted to tj minus 1 to tj. Now I will break our sigma here into the respective straight lines, and let me write it as this is equal to f of z minus f of gamma of tj minus 1 times, or rather integral of this function over sigma restricted to tj minus 1 to tj. Okay, so what have we established? We have established that the integral of f over sigma minus this partition. This is the same as this, and it is the same as this. That is what we have established. So this is less than or equal to the sum. Here the sum is from j is equal to 1 to n, j equal to 1 to n of the absolute value of integral of f of z minus f of gamma of tj dz, where the integral is over sigma restrict the straight line tj minus 1 to tj. Okay, now let us take the benefit of the choices we have made with respect to the TJs. What do we know about TJs? We have ensured that the gamma of Tj minus 1 and gamma of Tj are sufficiently close so that the absolute value of f of z minus f of gamma of Tj is going to be less than epsilon by 2 times the arc length of gamma by using the uniform continuity of the function capital F, which I have just scrolled up to. If you notice, I am underlining it in green. When this happens, we can always write our capital F of Z minus capital F of W to be bounded by epsilon by 2 times the arc length of gamma, and we will use that here. We'll use that here to write that this is less than or equal to, by again using the properties of the integral, this is going to be less than or equal to epsilon by 2 times the arc length of gamma. Notice that f of z minus f of gamma of tj is bounded by this number. Why is that the case? Because z is a point which is lying on the straight line path from gamma of tj minus 1 to gamma of tj, and therefore the distance of z to gamma of tj is going to be less than the distance of z gamma of tj to gamma of tj minus 1, or maybe tj minus 1 is what I should be putting, because that is what I had been using earlier. It doesn't matter, one of the two should have worked, and that distance is less than the number which ensures that the difference f of z minus f of gamma of tj is less than this number in the box. Okay, so this times, we are not done, the arc length of sigma restricted to tj minus 1 tj, which is exactly equal to sigma of tj minus sigma of tj minus 1, because it's the straight line path. We know the arc length precisely in this case. But sigma of tj is exactly equal to gamma of tj for each j, and this can be written as by epsilon by 2 times the arc length of gamma summation j is equal to 1 to n mod of gamma of tj minus gamma of tj minus 1, which is bounded above by the arc length of gamma. Now you can see why I had put this gamma, arc length of gamma, in the denominator. So what have we estimated? So we did some estimation. What did we estimate? We have estimated this particular thing in the box to be bounded by epsilon by 2, which is precisely this object in the box. The first one has already been estimated by epsilon by 2 here. So what we have essentially proved is that the integral of f over gamma minus integral of f over sigma is less than epsilon by 2 plus epsilon by 2, which is less than epsilon. Let me write that down. Hence, integral of f over gamma minus the integral of f over sigma, this is less than epsilon, and we are done. The condition here, so let me now go back to the fundamental theorem of calculus, which stated the hypothesis in this manner. We can now replace closed polygonal paths by closed rectifiable paths. Okay, that is good. Even though we did prove all these results with the greatest generality of rectifiable curves in mind, most of our applications will be restricted to curves which have much better regularity. Let me now give you two classes of curves which will be of greatest interest to us. They are very special curves with much better regularity. Let me define smooth curve. Smooth curves, rather, the class of smooth curves. So we say that a curve gamma defined from say AB into C is a smooth curve if gamma is continuously differentiable. So it's already quite powerful in terms of regularity. And this is not enough though. We demand that the gamma prime at t is not equal to 0 for all t in AB. The derivative or the tangent vector doesn't vanish at any point. If this criterion is satisfied by our curve, we say that our curve gamma is smooth. So notice that this notion of smoothness is not the notion of smoothness in the case of differentiation that we encounter. It can happen that our curve gamma doesn't have a second derivative. Smoothness in the sense of infinitely many derivatives existing does not necessarily get satisfied by smooth curve. So the notions shouldn't be confused. This is a very specific notion being defined for curves. So the straight line path, for example, is a smooth curve. Most of the curves we have actually encountered are smooth curves. In fact, we were writing down the circle equation of the circle. That's a smooth curve. Most of the curves, as I said, are smooth curves. Either smooth curves or what I'm going to write down next, contours. It will be either smooth curves or contours. We say that a curve gamma is a contour. Gamma from say AB to C is a contour if it is the concatenation of finitely many smooth curves. So for example, the polygonal paths which are obtained by concatenation of finitely many straight line paths, that's a smooth curve. So these two notions are more than enough from the point of view of practical applications. Even though we did define or develop our theory from the point of view of a much more general class of curves, one should keep in mind that this is more than enough for most practical purposes. Okay, let me stop here.